So briefly, the history of the discovery of radioactive materials. Like realizing these materials are radioactive came a lot later, right? People discovered these things a long time ago, and then if you read Greek mythologies, all kinds of other mythologies, they all mention radioactivity in there. Some sort of spirits, take the power away, take the strength away. There are places where radioactivity is a little higher, and like I remember when I was studying this, the history of this thing, in the Soviet Union, when they were developing nuclear weapon, they were trying to find out where they can mine ores, and an expedition found samples, and they spent a little bit too much time in the caves where they were studying the rock samples. And they're coming back, some of them got sick, and this was due to radioactive poisoning. But again, people did not understand this fully until after World War II, after nuclear bombs were used in Japan, and after many tests, people figured out, oh, there must be some danger just in the presence of the radioactive materials. So, but people knew somehow about these things long before they understood them. So, discovery of radioactivity is attributed to Becquerel, who placed. He was given a piece of rock sample, and they were trying to find new elements that would fit into the periodic table. And the sample of rock, he placed that rock in a drawer on top of some other papers, and he forgot about it. Sometime later, he opened the drawer, pulled up the papers. The papers, one was the envelope with undeveloped films, or rather photo paper. He used them, and he discovered there were lots of like black spots on the paper. So after it was developed, so he realized that the paper was ruined, and he was wondering why it was ruined. And eventually he discovered that the blame was on the rock. The piece of rock was emitting something, some sort of invisible light, and discovery of that, and then studying of that led to discovery of radioactivity. So now, how do people get from discovering radioactivity to figuring out how to make a bomb? So basically, you start off with now I'm not an expert in atomic bombs, so I'm not gonna like explain the whole technology, but like the science behind it is pretty clear. So basically what you have is some sort of uranium salts. Let's say uranium, I don't know, chlorine something, for example, I don't know. And they mine it, and they turn it into some sort of gas. So this chemical reaction turns into gas. The reason it turns into gas is that it's easier to purify gases. And in reality, uranium comes in form of uranium-235, which is feasible material, and uranium-238, which is not feasible. So most of this is non-feasible material, which means that it's a waste. So what they do is they use the fact that they have slightly different masses, and when you put it in a centrifugal machine, the light material will end up so basically, in a centrifugal machine, you will have gases separated so by the mass. So lighter material will fly out farther. So this will be like uranium-235, and the heavier material will be like closer. Let's see. Let's check if it's true actually. This is centrifugal force, centripetal force, but also centrifugal force. So if you have more mass, right? So you would need more force to keep it in a circle, right? And I don't know. Anyway, so somehow these gases will separate. Okay, and basically you continuously centrifuge these things, and eventually you get higher concentration of uranium-235, and then they turn this gas basically into uranium oxide. Again, I'm just making up the formulas. Maybe this is right, maybe this is not. It doesn't matter. So uranium oxide basically is a piece of ceramic, and it will be mixed with some filler, right? And the filler is done, this material is done, could be stored for a pretty long time. It will decay slowly, but it could be stored for quite some time. This could be used for atomic power or nuclear power plants. With the nuclear bomb, they purify it to, I don't know, maybe 90%, maybe 95%. So really high purity, and that takes multiple stages of centrifuge machines. And if you follow the news about Iran developing nuclear weapons, many years ago, there were always news, like centrifugal machines were always like the top of the news. And that's the main way to purify it. There's no other way to purify uranium. So once it's purified, then it has to be handled very carefully because it may reach so-called critical mass. Richard Feynman, at a very young age, was invited to participate in the Manhattan Project, which was initiated in Manhattan, basically. But then it was moved to south somewhere, Los Alamos, and he noticed one day that the temperature of the containers, and that time they were not using gases, they were actually using liquid. So it was liquid salt of uranium. They were reaching certain temperatures, and he was wondering why this tank of uranium salt solution was getting hot. And he ran some numbers, quick calculations. Again, physicists are really well trained and really good in estimating things, usually. And he discovered that slightly more of this uranium salt would lead to an explosion, not a nuclear explosion, but overheating of the solution may lead to sudden boiling of this liquid salt solution, and that could lead to a disaster. And they were collecting this uranium very carefully, trying not to lose, any amounts, so that concentration will become high enough for a bomb. So why concentration is important? So if you have uranium-235 and you shoot a neutron at it, so this is uranium-235. We talked yesterday, it will split, and then as a result, it will shoot out 3 neutrons. Okay, on average, 3 neutrons, 3 neutrons. So those can actually collide with other uranium nuclei if they're close by, right? So that means that they will create the next step in fission. So then this creates another 3 triplets of neutrons, right? And as a result, you get more neutrons. So basically, you end up with a 3 to the power n. And if every split takes a really tiny fraction of a second, then you can divide that second by number of splits per second, or the frequency rather, and you will find out basically what n would be equal to. So this n could be enormously big. So I'm going to put like, I don't know, some number. And obviously 3 to the power of infinity, or really large number, is going to be even larger number. So this is called chain reaction. chain reaction. And if you ever watched those competitions where people set up dominoes and they strike one of them, it leads to the whole chain of events. So it's kind of similar, but in this case, it's like a chain reaction where one reaction triggers the next 2 or 3, and the next one triggers the next 6, 7, 8, 9, and so forth. So the number of reactions per second per unit time increases exponentially. Okay, and every reaction releases enormous amount of energy, and obviously this creates an explosive release of energy. This is why it's an explosion, and that was the foundation for nuclear bomb. Now, if you have a lot of material concentrated in one place, then that could lead to trouble. And why is that? So basically, if you have like uranium here, it's split and it goes here, and it splits and it goes here and it goes splits. So you have so much material concentrated that it will lead to chain reaction. This amount of mass enough to initiate chain reaction is called critical mass. Critical mass. Critical mass means that the minimum amount of mass that is necessary to maintain chain reaction. So critical mass is the minimum mass required to maintain chain reaction. Now, it doesn't mean that critical mass will be explosive. So it may just maintain chain reaction. So like in nuclear power plants, you have critical mass, and once you initiate it, it will maintain, the chain reaction will maintain itself. And in case of nuclear bomb, you want the number of reactions to increase exponentially. So the structure of the atomic bomb is pretty simple. Let me go to the next slide. So what we have here is basically, let me see if I can zoom in. So first of all, you have critical mass, which is not connected together. So you have, let's see, we can make a, so let's see if I can do this. Okay, so we're gonna draw a circle. So I was told this is about the basketball size. So then we're gonna draw a thick line. A thick line, which will be, I don't know, blue line. Something like this. So we're gonna split, this is critical mass, that if you keep all the pieces together, it will explode. So you don't keep them together, you keep them separated by some material that will be absorbing neutrons. So the stuff is gonna be, oops, it's too thick. So this is neutron absorbing material. So it prevents neutrons from going through and then initiating more reactions. The quarter piece, or in this case, will probably 1/8 of the sphere, would be decaying over a long period of time. But the rate of decay is quite slow, so the weapon can be like in storage for a long time. Now, in order to push these things together, you need another sphere, which will be, let me see if we can make that. So this is another sphere, which will be filled with regular explosives. So let me just use different color. So this area will be filled with regular explosives, and they have certain designs that will make sure that the explosion will go, the force will be pushing in. So this is kind of a, whatever, regular TNT. So this is a regular TNT. Okay, so what happens was, excuse me, they trigger TNT, TNT explodes. The sphere around this is a very thick metal sphere. So let me make it really thick here. So this is a very thick metal sphere, very strong. So when explosion happens, explosion is first it pushes this fractions of the critical mass together. So they start fusing together, and so this creates implosion of the feasible material. So we can write it down. So explosion of TNT pushes pieces of uranium together to make or exceed critical mass. Critical mass. So when this happens, you have a chain reaction, the runaway reaction, and the uranium starts undergoing fission reactions and releasing enormous amount of energy. So because this happens so fast, not all of the material undergoes fission. In fact, it's a very inefficient way of releasing energy from uranium, unlike nuclear power plants. And most of the uranium will be actually evaporated due to the high temperatures and will be just, spilled over in the explosion. Only small portion of the mass is converted into energy. So how much of that mass is converted into energy, we can actually estimate this. So let's take an average 100 kiloton bomb. I'm saying average because today's bombs probably are in the order of megatons. The largest atomic bomb, or maybe nuclear bomb, maybe a hydrogen bomb, I don't remember, that was exploded was in the order of about 200 megatons. And Russians exploded this bomb. It was called Tsar bomb. Initially, they wanted to make it 500 megatons, which is not a really big problem because, like, once you reach a certain level, then you can make basically any power, bomb of any power. And the concerns were, quotation mark, concerns were that there would be radioactive, fallout, and they made it a little less powerful, right? But radioactive fallout was happening everywhere and anyways. So let me see what's the power TNT is. TNT energy in joules. Okay, let's see. 1 gram of TNT in joules. Interesting number. 1 gram of TNT, they say it's equal to 4.18 10 to the 3 joules. That's very interesting. So one, okay, let's to kilogram. 1 kilogram of TNT is equivalent to 4.184 10 to the 6 joules. 6 joules, right? So 100 kilotons equals to 10 to the power of, so 2 zeros from here, 3 zeros from kilo, and 3 zeros from ton. So 2 plus 3 plus 3 will be 8 kilograms. Okay, so let's multiply these two. We will get the total amount of energy. So total amount of energy released in this case will be 4.184 times 10 to the 14 joules. Right? Is it correct? Confirm if it's true. 2 zeros from 100,000, 3 zeros from kilo, 3 zeros from ton. 1 ton is 1,000 kilos. So 8 zeros in addition to 6 zeros, that's 14 zeros. That seems to be true. Okay. So now we're going to equate it to mc squared. And what I'm going to do, I'm going to move all these nodes to the left so I have space over here. Okay, so c is the speed of light. Okay, please calculate the amount of mass that will be destroyed or converted into energy. So let's see. Okay, so how much mass will be converted into energy? Boo, Tazin, this is enormous. If this was true, the whole Earth would be destroyed. The Earth would be like cracked into pieces and thrown out into space. Sorry, Earth, we just destroyed you. Run your own numbers again. You have to get the number on your own. That way you own it. This is kilograms, right? We're getting kilograms. So basically, it's roughly about not more than 5 grams. Yeah. So all of that is just to whatever, you know, this is just ridiculous. So we're getting 4.68 10 to the negative 3 kilograms. So roughly 5 grams. 5 grams of matter converted to pure energy is equivalent to 100,000 kilograms of TNT. How insane is that? Okay, so I don't know. This is so crazy. So people make a bomb, it goes off. Most of it doesn't do anything in terms of converting energy, mass into energy. 5 grams of that thing converts into energy, and that's enough to destroy like a mega city, basically. Atomic bombs we used in Japan, they were, I think, 50 and 80, something around that kilotons. So really low power, small power bombs. So today's bombs are much more powerful. They're much more compact, and they even lost some bombs. Like I think there are a couple of cases which are not resolved. Um, what's it called? B-52. They accidentally dropped one bomb, I think somewhere over Canada, and one was dropped somewhere in the ocean. I don't remember exactly all the details, but basically one of them was retrieved. The other they couldn't reach it. So it's still sitting there. It's like a ticking bomb. So, any questions about this? Let's check the time.